Hello, I'm Dingler, and this is my Lab 1 for Physics 2211 of our constant velocity. The purpose of Lab 1 is to display the properties of Newton's second law, or the momentum principle. Through the comparison of an experimental model and the computational model, we'll be able to view this. The computation model uses a given code and it's updated with initial values and velocity and position update formulas. The experimental model, we use a recorded video and then use the tracker program to compare the experimental model to the computational model. For the result preview, the experimental model slightly differed from the computational model, where we display the reasoning in the following slides. The key idea in this lab is Newton's second law. From Newton's second law, we can derive the following formula, the velocity update formula, which is V final equals V initial plus F net over mass times delta t. In our experiment, the F net is equal to 0, which will produce a constant velocity throughout the experiment, as 0 times the delta t will always equal the initial velocity. From this, we'll be able to view forces such as friction being dealt on the ball that would not occur in the computational model. The system for this lab is the tennis ball, while the surroundings include everything else other than the tennis ball. For the experimental model, I videoed a ball rolling across the screen. Using the tracker program, the ball distance was marked every 1/10 of a second from beginning to end. Using the information, the program displays a velocity graph, allowing a comparison to the computational model. As seen in the top right corner, the graph is a constant increasing velocity. For our computational model, we used a given glow script preset. From here, we set the F net equal to a 0 vector and included the velocity update formula as well as the position update formula. Using information given by the experimental model, we were able to create a model to directly compare its accuracy. Information added to the model included inputting initial position given by the experimental model as well as the initial velocity given by the equation VI equals delta R over delta T, using the R1 and R2 and T1 and T2. We also set T equal to less than 0.935 to align with the experimental model's length. This slide displays the results of our experiment. As seen in the graph, both data sets have a positive slope. The experimental data perfectly aligns with the computational data for the first half of the data set. From there, the experimental data slope slowly decreases compared to the computational's constant slope. This could be due to friction, air resistance, or a slight curve in the roll of the ball, which is not seen in the computational data. Possible sources of error include the ball drifting slowly toward the end of the roll sideways, making it not a straight and linear path. The precision of the markers in the tracking system could additionally not be 100% accurate. The slightly off accuracy could create a slight difference in the computational data's true set. If I were to flip the x-axis, the slope would become a negative decreasing slope rather than an increasing slope. For the what does it mean statement, setting the net force equal to 0 displays that all forces acting upon the object are balanced in direction and magnitude. This shows that at least two forces must be acting upon each other for it to sum to 0.